Hello, everybody. So let's talk about angular momentum. What we've come to is, our familiar looking equation for the sum of the torques about a common axis. And that was going to equal, we saw that as R common axis crossed into the change in the linear momentum P as a function of time. All right, so what we have to do here is simplify the equation just a little bit. If I had RA crossed into P, and I took the time derivative of that, I would get the time derivative with respect to t of R A crossed into the momentum plus R A into dP dt. Okay, we talked about this as rigid body motion. So when we calculate the torque about an axis, the time rate of change of the position of the axis to the momentum doesn't make any sense. So this term right here is saying there's a velocity crossed into the momentum, and just by the rules of cross products, if I did I cross I for the terms within the cross product, we know cross products that are cross products of themselves always return a value of 0. So we can ignore this piece. And that allows us to continue our conversation about what torque changes. So the sum of the torque about an axis is equal to the time rate of change of RA cross the linear momentum. So what this might look like is, let's just grab a axis of rotation. It's going to map itself to a particular R about the axis, and then there's some momentum being carried. And what we want to know is the time rate of change. So what happens to RA if the momentum is now doing this? There's clearly a change between t equal 1 and t equal 2. And we need to quantify how that is changing. It's more than just the momentum that's changing, it's also the possibility of the distance to the momentum that is changing. As such, we're going to define a term called L, which is our angular momentum. And it's going to be a vector, and it's going to be defined as RA cross P total. And everything's going around the same axis. So that's the angular momentum. And it is at this point just a cross product exercise. So if you can do cross products, you just have to use the same axis and find the linear momentum total. You may recall back in the distant past that let's go purple, that we said we had the kinetic energy total for an object was comprised of its kinetic energy translational plus the kinetic energy rotational. And this was an example of when we had an object moving with a velocity down a surface, that we knew that from our axis, where we start, that at some time later, so T1, at some time later we'd be down here, same velocity, or different velocity depending upon the conditions. So there'd be a velocity at this point, and we know this thing would have been rotating. So we're going to get a rotation as well. It's the combination of the rotation and the velocity which makes this thing roll, provided we don't forget the no-slip condition that the velocity of the center of mass is equal to the radius of contact and then the angular speed. So what we'd like to do is see if we can't do the same thing with our linear momentum. Angular momentum. So we get our starting point. We'll call this T1. And we need to pick an axis. So I'm going to choose an axis off to the bottom here. Then, as the wheel, well, I'm not going to make it, spins, it's a very Fred Flintstone wheel. What I need to do to get LA total is to sum up all the RAs and all the momentums within the entire object. So I've got to sum up all of those cross products. I have to do an infinite number of cross products in order to figure out what's going on. And what's going on is complicated. I've got momentum's going this way, and momentum's going this way, and momentum's going backwards this way, and some momentums are going to be going down this way, and I need to have my R vectors, all of them going to those different momentums. So these are all the R's. So to find the angular momentum, that's what I'd have to do. Needless to say, this falls into the category of yucky. So let's try and be clever. Yes, it's often gotten me into trouble being clever, like when I hit the erase button instead of the draw button. Okay, so I'm still drawing. Great. So at time t equal 1, we have my axis set up, and choose the same point to measure r from, and then we've got, smart this time, the wheel rolling. So wheel rolling, and a velocity of the center of mass. So now LA total, let's compute this by first saying, just like we did for the kinetic energy, let's find the L translational. So this is going to be thought of as going from R is going to be from the axis of rotation to the center of mass. And it's going to take advantage of the fact that it's using the center of mass momentum to give us mass total velocity of the center of mass. Okay, so I've run out of screen, so I'm just going to write this as L trans, so we have it. And once we're at the center of mass, let's get the angular momentum around the center of mass. So the angular momentum around the center of mass is found by summing up all of the tiny little radii, and now I'm going to cross them into all the tiny little momentums. And I need to do a quick erase because that's supposed to be the dp. So one of the first things you'll notice is if I'm sitting at the center of mass, of some object that's rotating around me, every single velocity will be at a right angle, so it's going to be 90 degrees in there, between RA and V, or in our case, little mv. So I have the right angle, so I don't have to worry about the cross product. It's going to give us a direction depending upon how we integrate it. So let's integrate. Oops, can't quite do that yet. And we have to remember that the velocity is equal to r omega. So I'm going to get r times m r omega. So n center of mass says, what I'd really like you to do is to take the integration of m r squared and integrate it over all of the individual masses, because that's going to get me my velocity. Okay, so and dm and omega. The point of the L center of mass is we come away with something that looks like the moment of inertia times the omega. So we're going to come out with something that looks like I omega in whatever direction the omega is rotating. So what we've seen with this quick derivation is that the torques, summing up all of the torques that are acting on the system, is going to be equal to the time derivative of angular momentum total, which can instead be thought of as taking the time derivative with respect to t of let's see, so that's going to be Ra to the center of mass crossed into big P, which is the center of mass, momentum, plus the time derivative of I, moment of inertia, about the same axis as to which it is spinning. And omega carries a vector direction. So that's it. That's the that's the story of angular momentum. That if I apply a torque, I don't need to write that again. If I apply a torque, I would do two things to a system. If the system's center of mass is changing, so if that center of mass is changing, then I need to include this term. If the object is spinning on its own axis, I include that term. If it's doing both, I need the entire set. Okay, so that's our intro to angular momentum. I'll do a couple more little short worked examples to show you how it all comes together soon.